Hi everyone, today we're starting Unit 6, Thermodynamics. We'll start with topic 6.1, which is covering endothermic and exothermic processes. Now, before we can talk about what endothermic and exothermic mean and what that means in the context of chemical reactions, we first need to talk about the first law of thermodynamics. The first law of thermodynamics very simply says that energy can be transferred from one form to another, but energy can never be created or destroyed. This is very similar to what we've learned with matter, right? Matter can never be created or destroyed, and similarly, energy can also never be created or destroyed, but it can transfer from one form into another. For example, right, if we want to think of a real-world example of this, if we think of photosynthesis, energy from the sun is being converted into energy to grow plants. Plants will photosynthesize in order to make their own energy, but that energy first comes from the sun. The plants are simply not creating their own energy. Now, whenever we're talking about thermodynamics and the first law of thermodynamics, there's a few definitions that we need to make. The first is if we have any sort of a reaction happening in a container, we have the system, and this is essentially defined as what we are studying, and we have the surroundings, which is quite literally everything else. And so let's take this example over here to the right. The system here is the H2 and the O2. Right? It's the gas inside of this piston. This is our system. Our surroundings are literally everything else. It's the cylinder itself. Right? This is part of the surroundings. The piston is part of the surroundings. And all this air outside, that's also part of the surroundings. And so in our example, it's the cylinder, it's the piston, and it's everything else outside. So whenever we need to think about energy being transferred, we need to think about the system we're studying and the surroundings. Now we have a few different types of systems that we can be referring to when we're thinking of thermodynamics. The first is an open system. Now, as you might imagine, in an open system, we can exchange matter and heat with the surroundings. We also have a closed system. Now, contrary to what you might think, you can still have some exchange in a closed system. In a closed system, you can only exchange heat with the surroundings. So basically, not matter. So if I have a gas inside of a cylinder here, what can happen is the heat can be exchanged with the surroundings, but the matter itself cannot leave the surroundings in a closed system. The third system that we have is an isolated system. And in an isolated system, this is the case where we cannot exchange heat or matter with the surroundings. And so depending on the type of system that you're analyzing, we might have different scenarios happen where you can have heat or matter exchanging with the surroundings. The biggest things to remember: in an open system, we can have both matter and heat. In a closed system, it's only heat. In an isolated system, you cannot exchange anything. Now, of course, we're all pretty familiar with the concept of matter. It's anything that has mass, and so hydrogen, oxygen, any element on the periodic table, any molecule, whatever it may be, that has mass. That's what I mean by exchanging matter. When I'm talking about heat, which we define by the letter Q, is the amount of thermal energy transferred from something hot or something that's, of course, at a higher temperature to something that is colder. Basically, with a lower temperature. So all heat is it's the amount of thermal energy transferred from something hot to something cold. The units for heat are either joules or kilojoules. This is really important as we're starting to calculate something. We should know whether or not what kind of units we're using with heat. Now, knowing this information here, we can make a few definitions. A process is known as exothermic if heat is transferred from the system to the surroundings. So if my heat or my thermal energy is going from my system to my surroundings, then I have an exothermic process, and the heat is negative. Now, an endothermic process is the exact opposite. When heat is transferred from the surroundings to the system, then you have an endothermic process, and the heat is positive. So exothermic means it's losing heat. Essentially, the system itself is losing heat. In endothermic, the system is gaining heat. Now, if we have an exothermic process, just to demonstrate what this will kind of look like, if we have an exothermic process, let's say I have a little flask right here. I have this little flask right there. It's a poorly drawn flask, but it's a flask nonetheless. In an exothermic reaction, the heat, where heat is this in red, the heat is leaving my flask. And so the surface of the flask will feel hot, right? Because the flask itself is the surroundings. The system is actually the molecules that are inside of the solution that's in my flask. And so if I have a little solution here, right, that's my system. Everything else is the surroundings. And so the surface of the actual flask will feel hot. In an endothermic reaction, if I have that same little flask, again, poorly drawn, what's happening now with my heat is that my system is gaining heat. Right? My system being the solution, The system is gaining heat, or heat is going into the system. So now the surface of the flask will feel cold. And so that might seem a little bit counterintuitive, but if you have an exothermic reaction, your actual reaction vessel will feel hotter because the heat is leaving my solution, and so it's going into the glass. In an endothermic, it's exactly the opposite. My solution is absorbing heat, and so the flask is going to feel a little bit colder. Now, there's one situation where we're often going to see endo and exothermic processes. One of them that you're often going to see is the dissolution of ionic solids, and when you dissolve a salt or an ionic solid. So these can be both exothermic and endothermic, depending on the situation. And the reason for this is twofold, right? There's the energy required to separate the ion pair and basically break the ionic bond. Right? And so this is going to absorb energy. Right? You need to put energy into the system for this to happen. So this is basically your endothermic process, because this is absorbing heat from your surroundings. There's also the energy that is released when the ion dipole forces are established between the ions in solution and the water. This is basically releasing heat. And so what's going to happen here is you have an exothermic process. Right? And so when you dissolve a salt in water, there's two things happening, right? You have the endothermic process, which is breaking apart the ionic bonds. And you have the exothermic process, which is making the new ion dipole interactions, which help stabilize everything. And so you can have both endothermic and exothermic dissolutions. And so dissolution is endothermic, meaning it absorbs energy from its surroundings. The solution will absorb energy from its surroundings when the energy required to break the ionic bonds is more than the energy released when ion dipole forms. So if it takes a lot of energy to break those ionic bonds, much more than the energy that releases out into the surroundings when you make that ion dipole interaction, then you have an endothermic dissolution. Dissolution is exothermic, is the exact opposite. And so the energy to break the ionic bond is less than the energy released when the ion dipole interaction forms. And so in this case, if you're dissolving some sort of salt in water, whether or not it absorbs or releases energy depends on the energy to break the ionic bonds and the energy that is released when you make an ion dipole interaction. And so let's look at this little example here together. This is saying and this is from AP Classroom. For a classroom demonstration, a chemistry teacher puts samples of two different pure solid powders in a beaker. All right, so we have a beaker, we have one little solid powder here, and we have another little solid powder here. All right, we have two solid powders in a beaker. It says that they place it on a small wooden board with a wet surface. And so it's on this little wooden board, and we have some water molecules here, right? H2O, H2O. It's a wet, solid surface there. And then they stir them together, right? So they mix all of this together, maybe with a little stir bar. They say after a short time, the student observes that the bottom of the beaker is now frozen, and so this water here is now frozen. The teacher asks the students to make a claim about the observation and justify their claims. So it's saying which of the following is the best claim and justification of the student's observation. Well, what we notice is originally we have liquid water right here, and then eventually that turns into ice. That means the temperature of the surroundings has gone down. T of surroundings has gone down. If the temperature of the surroundings has gone down, by the first law of thermodynamics, the temperature of the system, or the energy of the system, must have gone up, right? Energy of the surroundings went down. That means energy of the system must go up. If the energy of the system is going up and the surroundings is going down, this must be endothermic. And so options A and B are immediately out because they're exothermic processes, and what we have here is endothermic because the outside, the surroundings, are getting colder. And so it says an endothermic physical change occurred because the freezing of the water is an endothermic process. The second one says an endothermic chemical change occurred because the temperature of the beaker and the water on the board decreased as heat was absorbed by the reaction. As we see here, right, it says that she stirs the contents of this beaker together, and as a result of that, the water has frozen. And so it isn't that we're freezing the water by cooling it down. This reaction is absorbing heat from this water, which then freezes the water. And so the answer here would be D. We have an endothermic process, and it's a chemical change because this reaction is causing that water to freeze. And so you're going to have a lot of potential problems like this where you're asked to look at the systems and surroundings of something and see whether or not it's endothermic or exothermic and think about the chemical change. We'll have more practice with this in class, but for now, that's all. Thanks, guys.